Today we're going to be looking at piecewise functions. We have seen them a tiny bit on some of the work we've done so far, but we need to really take a look at how do we graph them and how do we evaluate them. So mostly we've been looking at functions that are represented by single equations, but in real life it turns out functions are represented by a combination of equations, each corresponding to a specific part of the domain or a specific x values. These are what we call piecewise functions. A piecewise function is a function that is a combination of one or more functions. The rule for a piecewise function is written much differently than what we've normally seen. It's a different function for different parts of the domain. For instance, movie ticket prices are often different for different age groups. So the function for movie prices would assign a different value or ticket price for each domain interval, meaning that would be the age group. So here's an example, our first example of a piecewise function, right? This is telling me that this whole function, f of x, has these two lines that represent different parts of the domain. So it's 2x minus 1 if x is less than or equal to 0. So it's going to include 1 on this piece. And the second half is 3x plus 1 if x is less than 1. So here we would just make sure that if we were going to evaluate this for 1, we would have to plug it into this top equation. So let's go ahead and try some evaluation. Just be careful. So first you have to figure out which equation to use, and you never use both of them to plug in a number. Right? You're only looking for one value when we're evaluating. Okay, so let's find out when x equals 0. Well, I need to figure out which of these equations do I want to use. Well, 0 is less than 2, so I need to plug into x plus 2, 0. So 0 plus 2 gives me 2. That's the function value at 2, or at 0, excuse me, it puts out a 2. When x equals 2, well, these both have 2 on here, but recall, less than 2, this does not include that value, so this has the equal sign here, right? Greater than or equal to 2. So we need to plug 2 into this equation. 2x plus 1, we'll substitute 2 into it, and we get 4 plus 1, which is 5. Right, so the function value at 2 is 5. And actually that would be where this graph on the y-axis where it would start, up at 5. And finally, if x equals 4, well, here we're again in this greater than or equal to 2, so we're going to plug it into that same equation. 2x plus 1, but instead substituting in 4. Oh, pardon me, I wrote a 4 twice. Let me delete that. That should be a plus 1. So we get 8 plus 1, and that equals 9. So that is how we evaluate, right? Is first we determine which domain value the given x lies in, and then plug it into the corresponding equation. And do not use both. If we want to then think about what the graph of these look like, here we're just, this is the rule they've given us. And so when everything is less than 1, we're going to have this equation here is what we'll graph. And when it's greater than or equal to 1, then we use this function to draw the graph. And let's look at that. That's on the next slide. Okay, so here we can see that if we're looking at these two equations, right, this 1/2 x plus 3/2, that is this section of the graph right here. And it would have an open whole circle on that end of it, right, because it does not include that value. This on this side would have that closed circle because it is, it takes on that value from here on out. So when we're graphing these, it's basically, you just have to think about, okay, what is this equation? And then making sure that when we do graph it, quite frequently you'll graph both of these pieces and then you would erase the parts that are extras in the domain, and we'll see that later. Here again, we can also, and we've seen this when we were looking at continuity, is that you can have two equations and have this point of discontinuity, right? And as you can see here, when x is less than or equal to 2, we have this circle that is filled in, representing that it does take this value here. But then we do have a jump discontinuity because the rest of the function is defined up here. A piecewise function that is constant for each interval of its domain is what we call a step function. So let's look at an example of a step function. Here's a step function. It tells me that f of x equals 1 if I'm between 0 and 1, 2 if it's between 1 and 2, 3 if it's between 2 and 3, and 4 if it's between 3 and 4. Now, this is really interesting because let's look at this graph now. This is why we call it a step function, is it makes little stairs that go up the graph. And if you notice here, it included every beginning value, but not the end values, right? So we have closed circle open because we have this discontinuity. The function's defined up here. It does not include this point. So we can have step functions that look like that. We can also have a step function that's shifted to the left or the right. So you could have something like this where it says 1, 2, 3, 4, but it could change those domain values, right? And let's look at the graph of this one. As we can see now, instead of it being over in quadrant 1, because this had all quadrant 1 domain values, now we can see that it's been shifted over into quadrant 2 because of these given domain values. So this is really important when we're trying to graph any of these types of functions. We do have some special step functions. Two particular kinds of step functions. They're called the ceiling function and the floor function. And I see that my printout here did not quite print these correctly. The ceiling function is represented with an X with, I always say it looks like a little house with a ceiling over it. And then the floor function is this here where it has the X with a box underneath it, right? So this is the ceiling and the floor. And what this tells us to do is to take whatever integer we've put in there, and if it's between two values, so say for instance, if this was 5.5 and we want to know the ceiling function value of it, we would round it up to 6. We don't use rounding rules here. It's if this value is in between two integers, then it goes up to the next integer or down to the next integer. And that's this slide right here is basically talking about that. Let's see if we can take another look here now at evaluating. We won't look at those floor and ceiling functions too much. It's just something that's nice to know what that little weird notation means. So when you're evaluating piecewise functions, just be careful. Remember that if you're plugging in 2, you need to find the domain that it's going to fit into, right? So here 2 is in this x minus 1 for the rule. And then you would plug that in and get the value of 1, right? We'll only substitute into this section. And that's all examples for today for the notes. I will go ahead and I will make another video that goes over some of the homework problems.